Hi, so we're back and we are now almost ready to start talking about compressible flows, which is the next major topic we need to tackle. But before that, I thought before going on to compressible flows, I had promised I would say something about lift on a spinning body. For that matter, lift on an airfoil, any kind of body that has a circulation around it. And in particular, you remember I discussed top spin on a tennis ball. So I thought I would take a little bit of time to discuss this. It's not to do with compressible flows, not yet. It has to do with incompressible and inviscid flows, really. The only difference being we can add circulation. Viscosity can be added. So this is not, we're not yet discussing compressible flows. We will be doing this small thing and then going on to start discussing compressibility. It's just that this is one of my favorite topics, trying to demonstrate lift. So I thought I would take a little bit of time to expound on this very briefly. Right. So before even talking about what we are now specializing, remember, to incompressible flows, not yet compressible, right? And let us now return, before we add circulation, let's return to the problem of potential flow around a sphere. Remember, essentially we had said that problem of potential flow is essentially a solution of del square phi equals 0, the Laplacian, where where essentially u, the velocity would be equal to the gradient of phi. In other words, this phi is really the velocity potential, right? And in polar coordinates, you recall that we had written down the general solution to this equation. We had written down the general solution to this equation and applying the appropriate boundary conditions. There were two boundary conditions. One was that the normal velocity, so what we are doing here is we are considering a spherical body like so. And the two boundary conditions we had applied was that the normal velocity was 0 and the velocity at infinity was equal to the undisturbed velocity, which is like this. Right. So these were the two boundary conditions we had discussed, and so we had applied that to the general solution of del square phi equals 0 in polar coordinates, and we had obtained the solution. Now, the only difference we were doing now, the only difference in the treatment now is that we are adding a circulation, a clockwise circulation, this, to that solution. Right. So we are by hand we are forcibly adding a circulation to the flow. You have seen this diagram before. So we are adding a circulation gamma, capital gamma, to the potential flow, and that makes the velocity stream function, not yet the velocity stream function, to be this. Earlier we had just this much, okay, and now with the addition of the circulation we have this piece. So this is what is new now, due to the fact that we have added clockwise, this kind of a clockwise circulation to the already existing potential flow, right? So that's what we've done. So there's the new piece we've added, right? And notice, see the analogy between the gamma, this term, and a line charge in electrostatics. Remember, an infinite line charge, the potential due to an infinite line charge looks exactly like this. There's a logarithmic dependence on r, right? So the analogy is exact, right? So now this is the velocity stream function, and by the definition of the stream function, you remember how the velocity is derived from the stream function, right? So you take the curl, and so by the definition of the stream function, there's a relation between the stream function and the potential, and so by definition the velocity, the theta directed velocity, this kind of velocity, yeah, is equal to this, yeah, and that becomes, I beg your pardon, this really should not be, there's a mistake here, this should be So that's so you take the differentiation of this, and you can see that so it becomes this, right. So now the theta directed velocity becomes this, right. So remember, there's this funny term sigma gamma over 2 pi r. So there's a funny behavior when r tends to 0, but remember, as we had emphasized earlier, we are only talking about the exterior solution, the solution exterior to the sphere, and so so r equals 0 is of no consequence for us. So we do not need to worry about the pathological behavior of this piece of this piece when r tends to 0. That represents the interior solution, and that's another solution, and we don't have to worry about that, what it is. And now we allow only for tangential velocity at the surface. Remember, we are still talking about potential flow. The only difference being that we have artificially added a circulation to it. We are still talking about potential flow, and therefore we do not allow for normal velocity, we only allow for tangential velocity. Okay, that is why we can do this. But it is important to also recognize that we are indeed using the solution for potential flow, but we are really trying to simulate a non-potential or a viscous flow with this solution. Okay, so what's happening is the ball is actually spinning in the clockwise direction, and in a real situation, in a real world situation, there is finite viscosity, and as a result of the spinning, the fluid layers that are closest to the ball, the fluid layers that are really, so this would be the ball, and it's actually spinning like this. So what's happening is the fluid layers that are closest to the ball are actually being dragged along with it. My drawing's not very good, like this. So there's a little bit of dragging, but this dragging is effective only in a very thin boundary layer like this. Farther out, no dragging. Farther out, the flow is effectively potential. Very close by, there is a bit of a non-potentiality. Okay, but what we do is we retain the potential flow solution, okay, and we simulate the effect of this dragging by adding a circulation like this. By adding a circulation like this, that's what we're doing. And since we are retaining the potential flow solution while actually considering a solution, a situation where the viscosity is finite, definitely so near the boundary condition, but nonetheless, as far as the mathematics is concerned, it's still that of potential flow. That's why we can have tangential velocity at the surface, unlike it would be in a real world solution with viscous flow, where even tangential velocity is not allowed. Both the components of velocity vanish for viscous flow at the surface. But here what we are doing is we are looking at the mathematics of a potential flow in which tangential velocity is allowed, and so the tangential velocity at the surface, you simply put r equals a, in this solution, and you get this. Okay, so that's what you get. And you remember Bernoulli's theorem, right? So Bernoulli essentially tells you 1/2 u squared plus p over rho equals constant. Right? This is what Bernoulli is telling you. Right? And since the ball is relatively small, we don't have to worry about gravitational potential. Right? So from this, so this is constant. So what this is saying, meaning, so from that we get the pressure at r equals a. We can relate the pressure at the surface of the ball to the pressure at infinity. This is the pressure at infinity, like this. Right? So the velocity at infinity is this. This is the velocity far away. In other words, at infinity. Right? So that's the velocity far away, undisturbed by the presence of the ball Yeah, and this is the velocity very close to the surface. So that's how it works out. Yeah, and this is simply a consequence of applying Bernoulli's constant, right? And yeah. So the first thing to notice from this expression is near the surface of the ball. So this is just a constant, right? As is this, u is just a constant, and there's also just a constant. A is the radius of the ball. Yeah. So all of these are constants. Now, how does the pressure behave with theta, right? So the way theta works is this is theta equals 0, and theta increases like that, right? So theta increases in the counterclockwise direction. So like if you look at it that way, we can ask the question, is the pressure symmetric around theta? This is the key question to ask, right? So it is not. It is not, especially if you only take 0 to pi, the pressure is not symmetric around theta owing to the sine theta term. So now maybe there's a drag, there's a lift. If there's no symmetry, in other words, if the pressure on one side is different from the pressure on the other side, there is a force, right? So remember, the force is essentially the gradient of a pressure, right? So if the pressure is different, then if there's a gradient in pressure, there's a force. And what is that force? Essentially, it's a drag or a lift. It depends. A drag would be something, we normally refer to a drag as a horizontal kind of force, and we normally refer to a vertical kind of force as a lift, right? A drag or a push, we don't distinguish, it's the same thing. And a lift, upward lift or a downward lift, we don't bother, it's the same thing. Okay, one would just be the negative of the other. So because of the presence of sine theta term, we know that there is a break in the symmetry, and maybe there's a drag or a lift. Okay, now the symmetry of the flow precludes a drag, because you see this, it's symmetric like so. It precludes a drag. There is no way, because the flow is symmetric in this direction, there is no way there can be a force either in this direction or in this direction. Yeah. So there has to be either a lift like so, or either an upward lift or a downward lift. Yeah. Okay. So that's what it is now. Yeah. In other words, there's no x directed force. The force has to be along the y axis, where this is x and this is y. So the force has to be along the y axis. Why is there a force? Again, because there's a gradient in pressure. Well, the pressure is different below the ball and above the ball. So naturally, grad P gives rise to a force, and this is the lift. Now, turns out that we can actually compute the lift. Okay, so what are we really doing? We are saying that here's a ball that's spinning like so. That's spinning like so, and as a result, it experiences a lift like this. That's what we are really saying. Okay, and we are now trying to compute the magnitude of this lift. Okay, so what are the dimensions of pressure? Pressure, all we have is a pressure now, yeah, and you take the gradient of that pressure and you get the force, right? But now the other way to look at it is that the dimensions of pressure, as we know, force per unit area. Yeah, we know this. And in spherical polar coordinates, what's a differential area? A differential area is something like r sine theta d theta. That just comes from this. Right. It's really the length of this L times r, but the L can be approximated as, if this is r. Right. L can be approximated as r sine theta, but this is r sine theta. So it's really r sine theta d theta. Okay, and that's what we have written down here. where the A is really the R. Yeah, we really concerned with the pressure at the surface of the ball. This is A. The radius is A, and we are concerned with the pressure right here. Yeah, so that's why instead of the R we have an A. So this is the area element, yeah, and then so this is P ds essentially. Yeah, and in particular we are writing down the P at R equals A. Yeah, and we integrate this from 0 to 2 pi, and that is what we call the lift pressure. So that's a force essentially, pressure times area, that's a force, that's a lift force, right? So substituting this value of P R equals A, I am simply repeating this from the previous slide, substituting for this in here, we get this magical formula. This entire, all these complications magically vanish away when we do the integration, and you get this very nice formula for the lift. Okay, it depends upon the velocity at infinity. Remarkably enough, it actually depends upon the velocity at infinity. Yeah, it depends upon the density of the fluid that you would sort of guess, right? I mean, if the fluid is less dense or more dense, I mean the lift would be proportional to that. This you can guess from intuitive considerations as well. And not surprisingly, it depends upon the circulation. In other words, you spin the ball viciously, you spin the ball a lot, and you experience more topspin. Yeah, you spin the ball a lot and the tennis ball experiences a larger force downwards, as opposed to if you spin the ball, not so much, the downward force is not that much. That's what this term is saying. Yeah, but interestingly, it also depends upon the horizontal velocity, the velocity at infinity, or the undisturbed velocity. Okay, and so this lift, as it turns out, although we have derived this particular result only for a spherically symmetric situation, turns out that this result, it actually holds for any shape, not necessarily a sphere. And this particular thing I am not going to show you, I am simply stating it. And this is when obtained more generally, in other words, when this result is obtained for a general shape, not necessarily a sphere, this is called the Kutta-Joukowski lift theorem. So this kind of finishes our small discussion about lift, and so from now on what we are going to do is we are going to start talking about compressibility, right? So we are done with talking about incompressibility, and from now on we are going to start talking about compressibility. We have just finished discussing lift on a spinning ball, and that pretty much completes discussion of potential flows, incompressible flows, and we've also done a fair bit about viscosity. Now we turn our attention to compressible flows. This is a bit of a major shift, paradigm shift from what we've been talking earlier, and really this is something that astrophysicists mostly concentrate on. Okay, when you look fluid dynamics books that generally talk about gas dynamics, these are the ones which discuss compressible flows, roughly speaking. Okay, and whereas most engineering applications, well, aerodynamics sometimes you do start venturing into compressibility, but most other engineering applications, flows past nozzles and so on and so forth, they don't bother about compressibility. It's not so important to them. Okay, incompressible flows are good enough, whereas in astrophysics, compressibility effects are very, very important. Now, before starting to talk about astrophysics, let us, can you think of an everyday situation where compressible effects are very, very important? Well, let me tell you, the speed of sound, or rather, sound waves. which is how what I am talking reaches you eventually, right? The waves, the sound waves are a consequence of compressibility. No compressibility, no sound waves, right? Why? Because sound waves are all about density, density compressions and rarefactions, isn't it? You know, I'm talking, and what I'm really doing is I'm setting little density compressions and rarefactions in motion, and these things are, if you were sitting in a classroom, they would directly reach your ears, and you would your eardrums would vibrate in response to these density compressions and rarefactions, and then it would get conveyed through a series of truly wonderful transformations and reach your brain, and your brain would figure it out as sound. In this case, what's happening is the density compressions and rarefactions that I'm generating are reaching my microphone and being converted into electrical signals and being recorded, and then the electrical signals are when you're listening to it on your laptop or your phone or so on and so forth, those electrical signals are being converted back into audio vibrations, again density compressions and rarefactions, and those are reaching your ear and you're hearing them. But the point I want to make is, here is an everyday example, okay, of compressibility. So compressibility is central to lots of things, in life, like sound waves, right? And so one of the main things we will do as we go along is derive the speed of sound, essentially, and you know this very well from maybe the 11th grade onwards. You know that the speed of sound generally denoted by C sub s is given by where P is the pressure and rho is the density, right? So we will derive this. We will see where this comes from. Okay, so that's our basic, our first goal. We will figure out how is it that the speed of sound, which is essentially the speed at which small disturbances travel, is always this. Okay. Afterwards, what we will do is we will say, well, how about speeds, how about flows where the flow is slower than the speed of sound, flows that are slower than the speed of sound, right? And so these are called subsonic flows. Okay, and flows that are faster than the speed of sound. These are called supersonic flows. So these are the two kinds of flows that we will concentrate on, and we will also we will see that supersonic and subsonic flows are very different in character. Okay, and they're very different in character, and we will also investigate this peculiar phenomenon where a flow can transition from subsonic to supersonic, and we call the transition between sub and supersonic flows. This is very important, okay, because like I said, the character of these two kinds of flows are very different. So when a flow transitions from sub to supersonic, these are called transonic flows. In other words, these are flows that transition from a subsonic flow to a supersonic flow, because the character of these two kinds of flows are very different. You have to pay special attention to flows that are transonic, and you guessed it right. Why are we mentioning this? Because transonic flows are very important in astrophysics. Examples of transonic flows are the solar wind, also certain kinds of accretion onto compact objects such as black holes and neutron stars. All of these are examples of flows that can be transonic. Okay, and transonic flows need special attention because the character of the flow changes substantially while going from sub to supersonic. So we will discuss all this when we take up this subject in some more detail. Thank you.